Okay, so now that we know about the levels of organization of biology, now we progress into, let's see here. So we know our levels. Now we progress to that first step. So this is a biology class, right? Let's not mistake that at all. But in order for the biology to make sense, we have to have some underlying knowledge, a foundation of physics and chemistry. And I've always thought they taught the sequence in the wrong way. Maybe this happened in high school. Maybe you took first semester, freshman year, biology. And then next you took chemistry. And then you took physics. So that is not the correct sequence, right? For it to make the most sense, it would be most logical. We learn the foundation first, physics, the energy, energetics, then the molecules, the atoms, the reactions, and then the biology would make more sense. But it's not taught that way. And I wish it was. I wish those were prerequisites, but they're not. So to try to make sense of the biology, I got to get us up to the level where the chemistry and the physics then are there in position to allow for our knowledge of biology to grow. So if we make the analogy here that we're looking at this piece of cake or whatever, the bread part, the different layers would be represented by physics and chemistry, right? And then the delicious topping up here, that would be then the biology. So, but this is sustained up, this is held up, it's supported by the foundational basis of the bottom, the bread, in this case, the physics and the chemistry. So we're gonna have a little crash course now in basically chemistry. This is not a chemistry class again, but we gotta speak the vocabulary, we gotta speak the chemistry language, and know some basic fundamental concepts of chemistry. So when we're looking at the atom, right? So the atom is the fundamental unit of matter. Okay, so what is matter? Matter is anything that has mass and takes up space. And then we can, well, what is mass? Right? It's not where we go Sunday morning maybe. This is mass is the measure of the quantity of matter. So we kind of start to get a little bit circular in our definitions. To phrase it in a different way, right? Matter, anything that has mass, anything that weighs something and that has some sort of volume that takes up space. If you think about it, well, that's pretty much everything around us, right? Maybe the laptop or the computer that you're looking at, right? Does that have weight? If you put it on a scale, is it going to weigh something? Does it take up space in the backpack? Yes. So your laptop is comprised of matter. It's a type of matter. Your pens, your pencils, your shirt, your pet dog, right? You, right? Us, individuals. So are we atomic? Seems kind of strange. Maybe you're having a low day, like, man, I feel kind of low today. You shouldn't, because you are atomic, right? We are atomic. We are made up of these atoms. So we matter. You are matter, right? So these are important concepts that we deal with, right? So pretty much everything around us is atomic, except some key, very big exceptions, important exceptions. If you can envision light, right? Can I capture light? Can I weigh light? Does light take up space, right? Light is a form of radiation, right? So radiation does not fall within the idea of being atomic. It's not a type of matter. And we're gonna talk a little bit about that more later in the semester. We're just trying to establish some important vocabulary terms here. So yes, we're looking at a very small level, the atom, but even the atom can be subdivided into smaller components, right? And we're gonna talk about protons, electrons, and neutrons, these subatomic particles. Protons would be then these positive charged particles in the center of the atom, what we call the nucleus of the atom. Neutrons also in the nucleus of the atom, but they are neutral charge. And then we have electrons that are high energy, negative subatomic particles that are sort of orbiting around the nucleus. They're very high energy type of particles. So if you can envision your favorite cartoon character, right? Mine when I was a kid was the Tasmanian devil, right? His little legs would get going super fast. You see like these little blurs. If you can visualize this, the better imagination that you can apply, the more better understanding that you'll have here, right? But here we're looking at spinning electrons in one sort of level, one plane. But can you envision those electrons going behind the screen and then coming out in 3D towards you? So it's this three-dimensional sort of sphere of energy. And that's this orbit in which the electrons will be traveling in. So again, protons. Again, protons have many problems apparently, but protons stay positive. So be like a proton, right? Be positive. Protons are positively charged. Right? Electrons negative and neutrons neutral or no charge. Some important physical law, right? From the laws of physics. The attraction of charged particles, the repulsion of charged particles. If we're looking at the same charges, so if I have a positive and a positive charge, they don't tend to do very well together. They tend to repulse away. Think of maybe, I don't know what relationship you have with your parents, but maybe you and mom or you and dad seem to always just be clashing. Well, maybe because you're too similar, right? So you think the same way or somehow, right? So if mom is stubborn and you're stubborn, it's not going to work too well. So same charges typically repel each other. Opposite charges tend to attract each other, right? Not tend, they do attract. So opposite charges attract, same charges repel. So these are important physical laws that are going to have important sort of effects on the actual atoms themselves. So we do have all these charges, right? There's positives here, there's negatives here, and we have all of this sort of either attractiveness or repulsiveness that's going on in these atoms. So I like when artists draw these pictures, they make them look, oh, look, just so picture perfect little atom there, like a picture perfect family, right? I don't know who this family is. I stole that off the internet, but they look all happy, right? Now, just like this is so picture perfect and this is so picture perfect, I'm gonna guess that's not 100% reality, right? Maybe before the picture or after the picture, these little guys are gonna be fighting, right? The kid's gonna be crying. Grandma's gonna get mad at grandpa or whatever the case, right? So imagine your family, like there's always a little bit of drama that goes on in families. Well, same thing with the atom. So it looks picture perfect, but right here, I hope you notice, we have a little bit of drama that's going to happen right here. Why? I back up. We have same charges. Same charges. So we have the actual core, the nucleus of this particular atom that is wanting to break apart, is wanting to sort of repulse each other apart. So luckily for us, that these peacemakers, these neutrons, are in place. So I don't know if you've ever maybe tried to get your friends back together. They were fighting. You can't, no, you know, they didn't mean to call you that. It's okay. Don't be mad. You try to, you know, bring peace, bring harmony back. That's sort of the role of the neutrons. So they're no charge, but they help to minimize the repulsive force of the protons. And if the electrons weren't so hyper, there would be then that force where the electron would be sort of brought into the proton. But there's so much force that there's so much, I should say, hyperactivity that it overcomes that attractive force there. So the electrons are able to be kept in their orbits, just like the moon stays in the Earth's orbit, the sun, or I should say the Earth stays in the sun's orbit. It's kind of like a miniature solar system all packed into one here, right? So, but a lot of chaos happening in that one particular nucleus, in that one particular atom. So if you ever have a little bit of drama in your life, hey, it's not my fault, it's my atoms. My atoms are dramatic, right? I don't know if that's a good excuse, but it's worth a shot there, right? So the idea of the nucleus, the atom, repulsiveness, harmony keeping, high energy orbits, that kind of stuff. So a lot of stuff going on in one single atom. Another term that's going to be used a lot is the idea of the element. And if you think of element, elemental, elementary, right? It refers to something very, like elementary school, the first school you went to, something very fundamental, very early on. So an element, you can read the definition there, but elements are basically specific types of atoms. So it'd be like me saying, like a dog. Well, there's different types of dogs. So there's dogs, but we can say, well, there's a Chihuahua dog, there's a bulldog, there's a German Shepherd dog, there's a mixed mutt dog, whatever, right? But so the elements are kind of like the flavors, kind of like the variations of the atoms. The elements have their protons, a very particular type of number of protons. They're elemental, right? It's like they can't be changed in any way. They exist in nature, and they are those particular elements, right? So each element is distinguished by its atomic number. Important. That's a test question right there, right? Ding, 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 ding. Test question, right? How do we distinguish different elements? Each element is distinguished by its atomic number. And what is an atomic number? Atomic number is the number of protons that we find in the atom. So the number of protons help define the element as the particular element. And each element has a different number of protons, right? So silver would differ from gold. Gold will differ from aluminum. Each one of these is their own element because they have their own type of atomic number. We don't have this big periodic table in front of us here, but if we were in lab, if we were in class, we would have this big chart there in the back of the room. And the periodic table, see if I have the periodic table will look something like that, right? And the periodic table has some important information for us. And again, this is not a chemistry class, so I'm just gonna skim the little top of the surface there. But within each little sort of block here, we have some important information, right? One, we have the atomic number. Oh, that's important. What was the atomic number? Atomic number was the number of protons, the defining characteristic for each particular element. So if the element has 2 protons, it has been defined by chemists as being helium. So we have the atomic number, then we're going to have a little chemical symbol. Might be 1 letter, might be 2 letters. The letters might make sense. The letters might not be intuitive, but this lets us know that we're looking at helium, right? And then we have another number down here, a bigger number. This is called the atomic mass. If I was to take 1 atom of helium, put it on a tiny little scale, it would give me a weight of about 4 Daltons, or about 4 atomic mass units. AMUs, atomic mass units, or Daltons. Very, very tiny measure of mass here, right? So what this number is the number of protons and the number of neutrons in the atom. Now you think, well, what about the electrons? Right? Well, electrons, they don't stay still enough. They're too hyper. And their mass is so tiny compared to the mass of the protons or the neutrons. So they're not factored into the mass, but they are there, yeah? And if we go back to our physical laws, if we have a proton, we know that that positive charge is able to attract a negative charge. So as the elements exist in nature, they're typically balanced. We have an electrical balance. For every positive charge, we will match that up with a negative charge. Positive, negative, positive, negative. So for the case of helium, we have 2 protons which can attract 2 electrons. And then we would have to mathematically solve for the number of neutrons. So to find the number of neutrons, we know that we have 2 protons. We know we have a mass of 4. So 4 minus 2, 4 minus the 2 protons leaves us with about 2 neutrons. And in chemistry and physics, they're real picky about, all the significant values, that, the decimal places. Biology, it's close to 4. 4.003, that's close to 4. We'll go with 4. Yeah. So we always round to the nearest whole number, and we keep the math simple there. But I hope this is making sense as to how we would navigate through the periodic table. So again, I think it's relatively easy math, right? We would basically just subtract this number from this number to get the number of neutrons. We wouldn't have to subtract at all to determine the number of protons. All we got to do is look at the atomic number, and that tells us the number of protons. And then we assume that the number of protons is attracting the equal number of electrons. Yeah. So let's see if that makes sense here. So if we're looking at these common elements, the ones in blue, those are the ones we're going to deal a lot with in this course. So 1 is hydrogen. Let's see, 6 carbon, 7 nitrogen, 8 oxygen. 11, 11's maybe not intuitive. 11 is sodium. You think it was the letter S, but no, S is sulfur over here. This is derived from a Latin term, right? So if you speak Latin, it makes sense. But if we speak English, it doesn't really, it's not, logical necessarily. 12 magnesium, phosphorus, chlorine, calcium, and another strange one, right? K. K is potassium. And you think, well, why not P? Well, they use P over here for phosphorus, right? But it's just a little bit odd. And again, if you were in a chemistry class, you would learn all of the other elements. But for biology, again, we spend most of our time up, say maybe 1 through 20, and not necessarily all of them. We deal with 26. 26 is not faith. It's not Fe in Spanish is faith. This is iron, right? And if you know of our blood cells, we have iron in there and the hemoglobin. So it's a very important element as well. But all of these distinguished by different numbers of protons, right, for the periodic tables, atomic number. Now, why should we care? Why should we know about chemistry? Say, I didn't sign up for a chemistry class. I signed up for a biology class. Well, if we want to know about the body, if you're going to be trying to understand how to fix a building, fix a car, well, we got to know the parts, right? If we're going to try to fix the body, we got to understand that the body is nothing more than a bunch of elements, right? This is kind of like the ingredients for a human. We're about 65% oxygen, about 19% carbon, about 10% hydrogen. So once we understand that, yes, we are made up of these elements, it makes sense then why we should have a very basic knowledge on these elements. You might know a little bit about antibiotics. Right? Antibiotics are important. They kill bacteria. They make us feel better. But what is an antibiotic? It's just a particular arrangement of elements, nitrogens and oxygens and carbons, right? So, and how is this different than aspirin, right? It's different shape, different complexity, but again, just a different arrangement of elements. Just like we can arrange alphabetical letters in different ways to get different words, to make different sentences, different paragraphs, different meanings, we can arrange the atoms, the elements in a particular way to make different types of molecules and medications. And something I like to study, right? Venoms. So what is snake venom? Right? Snake venom is nothing more than a bunch of elements arranged in a different way. Right? And when these elements interact with our elements and they change the, the proportion and the activity, the action of our biology, our physiology, it causes a very harmful effect for us, right? So again, we should have the understanding that yes, we do need to have a basic knowledge in chemistry to really understand the role of chemistry within biology. Right? So an important basis here. Different medication, but again, just different elements arranged in different sort of three-dimensional positions there. So to summarize again, our atomic structure is comprised of protons, electrons, and neutrons. Right? If we notice the very first, the smallest of our elements, it's a little bit, different than the others. And my question would then be why? Why do we not have a neutron in hydrogen? You see, we have hydrogen with the atomic number 1 because it has 1 proton, and 1 proton can attract 1 electron. But why no neutron? We have neutrons over here in helium atomic number 2, which can attract 2 electrons to its 2 protons, and then requiring some neutrons to help out there. And why do we not have neutrons over here? Again, there's no need. There's no repulsiveness, no repulsive force in the nucleus of hydrogen because it's only 1 proton. Right? So these are the kind of sort of knowledge, the kind of knowledge that I want you to have as we progress through chapter 2, right? And the why this, why that. So these are the kind of questions you're going to see on your exams here. A little video I'll try to upload on Blackboard. So in your notes, you should have this little sort of matrix here. It's not for a grade, but I encourage you to take the time and try to fill this out completely, right? Get comfortable with the vocabulary, get comfortable solving for this, because you will be doing this on the homework. You will be doing this on the first exam as well. Right? I've uploaded the answers as well, but I hope you don't cheat. Don't cheat. Don't look at the answers. Try to solve first, and then you can compare to see how accurate you were with your answers there. So with that, let me stop this before this file gets too big and too hard to manipulate. That's what happened with me yesterday. So trying to break these up into smaller files so I can, so they don't take so long to upload and stuff like that. But so I will continue, but let me pause this at this time.